So today we are going to be discussing the factors that affecting the capacitance of the capacitor, okay, and some other things as well. Can I make it here? Nope. Actually, I have to add another page. Okay. So, if we since we have discussed the concept of the basic concept of the capacitance and the capacitors, right now, if I have a capacitor, okay, so how the capacitance of the capacitor varies with the potential difference, okay? So we know that this is the equation Q is equals to CV, okay? And if I ask you to draw the graph against, okay, so okay, I'm drawing the graph of Q most of the time in millicoulombs, okay, and volts, okay, and sometime the vice versa, like this, okay. So can you guys recommend or can you guys suggest the shape of the graph that can be formed? Yes, anybody? Who can anybody suggest how the graph looks like? Anyone? Nobody, no one. Okay, so it should look like this. If you compare it with a straight line, since we are drawing it Q and V graph, so Q is on the y-axis, okay, is equals to mx, okay, and so this is how the graph look like, okay. And plus C, we know that C is a y-intercept, and over here no intercepts, so the graph can start or the graph start from origin, okay. So we can say that the graph would be like this, okay, where the gradient of the graph gives me the capacitance of the capacitor, okay. So the gradient over here, gradient is going to be the capacitance, okay. And if we have or if we just switch the axis, okay, so let's say I have the voltage on the y-axis and the Q in millicoulomb on the x-axis, so the graph will still be the same, but this time the gradient will going to be different, okay. And gradient will be 1 over 1 over c, okay. So this time the gradient would be 1 over the capacitance, okay, right. Now if maybe if the graph may not start from origin, then there should be some sort of systematic error in the in the measurement of capacitance, right? So that's why it may not start from zero if it is, okay. So by the way, this is the concept of the gradient. Now if we talk about the concept of the area, so the area of the graph or the area under the graph, we're going to, okay, fine. So this will going to give me the energy basically, right? So area will give me where you are. Okay. So the area will going to give me the electrical energy, right? Is stored in the capacitor, right? So these are the two things, right? Now, if we try to find out the area, so the area will going to be E is equals to 1 over 2 Q into V. Okay, this is the first formula, by the way, right? Now, if if you and you know that Q is equals to CV, so if we put Q into its value, so we will end up getting 1 over 2, and in place of Q, if I put CV, so it looks like this. Okay, now it become E is equals to half CV squared, right? So you can use this formula in a scenario, in a case where you have the capacitance constant and the voltage is varying. Okay, so if you increase the voltage, there will be more energy stored across the capacitor or stored in the capacitor, and if you decrease it, so you'll get the less energy, right? So this is the concept. Now the third thing is, that if we put the similar formula in V instead of Q, so it will gonna give us Q over C equals V. And then if I put E equals to half C, sorry, half into Q remains the same. And in place of V, you can substitute Q over C, right? Now, so at the end, we'll end up getting 1 over 2 into Q squared over C, okay? Or 2C, okay? Mainly in calculation, most of the time we use this formula for the energy, right? But both every formula can be used, okay, according to the given things in the question, right? Now, also keep in mind, if they're asking you to find the area of a specific region, okay, let's say this is a graph, okay, and they're asking you to find the areas, to find the energy stored when the potential varies between A and B. Okay, so let's say this is A and let's say this is B. Okay, so to find the energy stored um in capacitor between A and B, okay, between A and B, you'll have to apply the concept of trapezium. Okay, so this is going to be the length, okay, and this is going to be Q1 or QA, let's say QA and QB, QB, right? So you can apply 1 over 2 into, since the capacitance is constant, so you can either use CV squared, either you can, okay, fine, let's just use the trapezium formula. So from voltage A to voltage B, we can do sum of the parallel sides, that is QA time plus QB, okay, into VB minus VA, right? This is a trapezium rule, right? Or let's say this is change in V, so I'll be putting the change in V here, okay, to make the formula more easy, right? So this is the concept of the capacitance, or this is the concept of the change in energy stored in the capacitor in this region, right? So yes, now if you want to apply the second formula, then the second formula would be easier than the first one. Okay, for the change in energy, you can use half C VA squared or VB squared minus VA squared. Okay, so these are the formulas for the change in energy. Okay, right. So these are the formula for change in energy. Right now, we have another thing, that is the concept of the factors affecting the capacitance, right? Because when we see the formula, that is Q is equals to CV, so neither Q nor V will going to change the capacitor, right? So if you increase the voltage, there will be more charge stored on the capacitor, and there will be greater energy storage, right? And if you decrease V, or if you decrease the Q, then V will ultimately be lesser, or we will ultimately required in the less amount. Okay, that's why there will be lesser energy stored, right? So Q and V does not decides the capacitance of the capacitor. Okay? Once the capacitor is made, now the capacitance remains the same forever, right? But the factors that affect the capacitance are three factors mainly. Okay, first one is mm, so if you look at the formula, C is equals to epsilon naught A over D. Okay, so this is the formula that contains some variables, okay, the that decide the capacitance of the capacitor, right? If I ooh, that's good. थोड़ा सा नीचे भाई, just get down. Perfect. Okay, so now these are the three things that I have. Okay, and so these are the three things that I have, okay? And these are the main three things that the capacitors are actually depend upon, right? The first one is the um, the first one is the epsilon naught, which is basically the medium between the capacitor, okay? Although in our case, or in most of the cases, epsilon naught remains the same, right? But over here, the first factor that affects the capacitance is the epsilon naught, which is medium, okay? Okay, so medium between the plates. Okay, although in this formula, by the way, this is not a part of syllabus. Okay, it's just an extra thing to remember. Okay, so it is a medium between the plate. Okay, this is the first concept. Okay, second one is the area of the plate. Okay, area of the plate. Come on, यार क्या हो गया? Area of the plate, right? And the third thing is the separation between the plate, right? So if you decrease the separation, there will be greater capacitance, okay? And if you increase the separation, there will be lesser capacitance, okay? Because if you increase the capacitance, you require more work done, and if more work done is not available, then then the charge capacity will be smaller, right? So, but by the way, these are the three concepts of or the three factors or parameters that affect the capacitance of the parallel plate capacitor, right? Now, just keep in mind, don't write that concept. Um, like the voltage or the charge, okay? Don't write the factor that affect this thing, right? So fine. Now, moving on to a very small concept, that is the second type of the capacitor, the concept of the spherical capacitor, okay? It is like very small in the concept, right? It is basically mainly connected with the previous chapter, but in this chapter they sometime gave it in 1 or 2 mark, okay? And the concept is really small, right? Okay, so so if you look at the capacitor, okay, so this is my capacitor that has a radius r, and I have like I've drawn some of the sparks on the capacitor, okay, that shows the energy is getting stored onto it, right? And now if I write the formula for the capacitor, which is Q is equals to CV, and from the previous chapter, if you remembered, so we learned the concept of the voltage, and that was V is equals to KQ over R. Okay, if you remember it, so then fine. If you don't, then this is the formula, by the way, 4 over 4 pi epsilon naught R. This is the formula where Q is a charge stored on the capacitor. Okay. Oh, sorry, on this spherical capacitor, and R is the separation. The rest of the things are constant, right? So if I put it back in the equation, so I'll get Q is equals to C, and I have Q times 4 pi 4 by epsilon naught r, and bracket close, right? So if you simplify, come on. If you simplify, so you'll end up getting q and q get cancelled, right? And you'll get q is sorry, c is equals to 4 pi epsilon naught and r, right? Now over here again, epsilon naught has a constant value, e naught has a constant value of 8.85 exponent negative 12. If you remember it, then fine. If you don't, then this is the value, right? And it's a constant, by the way, it is mainly mentioned in the first page of the paper. Okay, and while the only variable over here is r, okay, which is r is the radius of the sphere, okay, radius of the sphere. So it turns out that this the capacitance of the parallel plate, the capacitance of the spherical capacitor generally depends on its radius. So how big the sphere is will decide how much the capacitance will going to be, right? So we can say that capacitance of the sphere, capacitance of the sphere, just a second, please. Okay, back. So this is the derivation that mainly asked in the exam. Okay, so just remember this concept. Okay, they'll ask you in 1 or 2 mark. Okay, and it was previously asked frequently, but then in the middle, or like in 2015, 17, 19, it wasn't that much. But I think in 2023 or 4, they asked few questions on it. Okay. So we have done with a lot of different things, okay? And these are the basic concept of the capacitance, right? Now, the last thing is the capacitor. Okay. So the last thing is the combination of the capacitor in series and in parallel. Okay. This is the last concept. This is going to be the last concept of the capacitor. EU. It's not looking good. Okay, this is going to be the last concept of the capacitor, which we have to learn. And then the chapter of the capacitor will be ended up. Okay, so in this concept, uh, copy, just a minute, and paste. Ooh, shit. See, okay. So let's imagine the two circuits, okay? The two circuit, one is the series circuit and the other is a parallel circuit, okay? And in series circuit, we have, wait, oops. Okay. So in series circuit, I have three capacitor, okay, and in parallel circuit, I have again three capacitor, right? And we are going to be discussing how the things varies, or how the capacitance, voltage, and the charge relationship are in the circuit, right? So first thing that you remember, or that you need to recall, is the concept of the circuitry that you guys had studied in your AS level. Okay, that is the concept of series and parallel circuit. Okay, so in series circuit, we say that the current remains the same. Okay, current remains same. This is the first thing. Okay, and the voltage will going to be okay. By the way, so in capacitors, we mainly do not recommend current or refer current, rather than we use charges. Okay, so current remains same, so charges will also remain same, right? Now, the second thing is the potential difference, and the potential difference is going to be um, EMF, which is the total potential difference that you are inputting. So this is EMF, and this is, let's say, C1, okay, C2, and C3, right? Now, so the EMF is going to be add up, okay? So EMF is the total input is going to be distributed among V1 plus V2 plus V3, right? And this is the concept of voltage, by the way, right? The voltage will add it up according to the Kirchhoff's second law, the voltage law, right? And then the third thing is to find out the, by the way, the derivation is important, okay? So to find out the capacitance, the combination of the relationship of the combined capacitance and the individual capacitance will be then given by okay, let's just apply the formula at everywhere. So I can say that the total charge generated from the battery, okay, should be equal to the total capacitance in the circuit times the EMF. Okay, I can use this formula. It was a basic formula, Q equals to CV, but I'm just using the subscript for to refer the concept. Okay, now this total charge get distributed throughout the circuit, or get it's flowing through the circuit, but since we don't have any other junction, so it will be same throughout the circuit, right? So it will be same in Q1, C1, C2, and C3, right? Now, so we can say that Q total, Q total, Q total, and Q total, right? This is the concept that the Q remains the same, right? Now the second thing is if we apply the formula, so Q total, because it is the same for every charge, C1 and V1, and then Q total is equals to C2 and V2, and Q total is equals to C3 and V3. Say now, if I try to put that into my main equation, so if I make EMF the subjects, I'll get QT over CT. Okay, so QT over CT, right? For V1, you can say that Q total, because the charges remains the same and the voltage will be V1, sorry, C1 because I'm making V the subject. Okay, so the second case, okay, the third case, the third for the second capacitor, it is going to be T total, right? Because um okay, C total and C2, okay, and plus Q total and divided by C3. Okay, now you can cancel all the Q's out, so you'll be left with 1 over 1 over C total should be equal to 1 over one 1 over C1 plus 1 over C2 plus 1 over C3. Okay, so this is the concept of the capacitor in series. Okay, always keep in mind this formula is being asked frequently, okay, in your exam, right? So you should know how to drive this formula. By the way, this formula shows you that the capacitance in parallel is going to be the negative reciprocal of the individual capacitance. Okay, now for the parallel circuit, so for the parallel circuit, we have the EMF. We have the EMF, and that EMF is basically um, remains same throughout the circuit, right? Because in series circuit remains same. Okay, there's the first thing, right? Now the current and the charge get distributed at every branch. Okay, charges. Wait, come on. Charges um split into in or charges splits or distribute when they come on when they enter. Yeah, it should be split, not charges, or rather say distribute Good. When they are, when they enter in the junction. Okay. Okay. This is the concept, right? So we can say that Q total is equals to Q1, Q1 plus Q2 plus Q3, right? This is a simple concept, right? Now, in place of Q and Q and Q, if I can put the values like for Q1, I can say that Q1 is equals to C1V. Okay, I can say that Q2 is equals to C2V. Okay, and Q3. Okay, now if I put that back in the equation, okay, so I'll end up getting, wait, once some space, you will get, you can write the Q total is equals to EMF and then C total, right? And then if I apply that in here, so EMF times C total is equals to V1 times C1 is equals to V total times C2 and V3 times C3, right? Now we can cancel all the V's out, okay? And we'll be left with only one thing, and that is the EMF, sorry, that is C total is equals to C1, C1 plus C2 plus C3. Not V1, C1, okay? So this is the concept for the capacitance in parallel, okay? So always keep in mind that if we have the capacitor in series, so capacitor in series will always be the same as the resistors in parallel, and capacitor in parallel will always going to be resistors okay, will always going to be the resistors in series, right? Now these are some of the basic concepts. Okay, now let's try a question. Okay, where I have given you a circuit. Okay, this is like the most common question that you can ever expect. Okay, but before that, let me give you a question that is based on. Should I give you? Okay, fine, don't. Okay, so okay, these are the questions. Okay, this is the figure, and these are the questions that you have to answer. Okay, anybody that can answer the first part, please. Find the total capacitance. Yes. No idea. Okay. So if I have if I have to find out the combined capacitance, so the combined capacitance is going to be you have to sum up the capacitance in parallel. come on, microfarad, okay, and that 30 become parallel with 15 microfarad, okay. So in series, sorry, and then you can say 1 over C total is equals to 1 over 15 plus 1 over 30. Okay. And then if you simplify, it will be 15 times 2 over 50, 2 over 30, 3 over 30. So I'll get 10. So C total is equals to 10 microfarad. Now, the third thing is the total charge. The second thing is the total charge that can be produced by the battery. Okay, like by the battery, which means you have to do Q equals to CV again. Okay. So Q is going to be the total charge, and 9 volt is a battery, and capacitance is 30 microfarad. So Q is 27, okay, 27 to 70 microfarad. Okay, so sorry, not 270, 90, because it is 10, not 30. 90, 90. 90 microfarad, right? So this 90 microfarad is flowing in the circuit. It will get stored in the first capacitor, it will get stored in the second one, and the second, third one, and then it will pass through the battery, okay? Or basically it's coming out of the battery, right? So if I say in the third question, if I ask to state the change, to state the charge stored on any one plate of the 15 microfarad capacitor, then which means 15 microfarad capacitor is right here. Okay. And we know that this 15 microfarad is in series. So and in series we have the total current of 90 microfarad, 90 microcoulomb, not farad. Okay. So it's going to be 90. Okay, this is the, come on. So Q times V. So this is the charge stored on any one plate of the capacitor. Okay. Always keep in mind this is a charge stored on any one plate of the capacitor, because we discussed in the previous class that um we discussed in the previous class that the charge stored on the whole capacitor is zero, because equal amount of positive and equal amount of negative charge gets stored on each plate. Okay, so the net plate and the net charge will going to be zero, right? But we talked about the charge stored on any one plate, right? Now the fourth is going to be state the charge is stored on any one plate of 12 microfarad capacitor. Okay, so for 12 microfarad capacitor, which is right here, we know that the 90 microcoulomb is flowing in the circuit from this point to that point. Okay, and then it moves in this direction, and the other move in this direction as well, right? But over here you have to keep in mind that in parallel capacitor, I just added, and in series capacitor will be reciprocal sum. Okay, so over here, since these two parts are to be added, okay, so their resistance will be quite high, and this microfarad, 15 microfarad, has a lower value. Okay, so when it combined with the capacitor circuit of these two capacitors, so it will gonna give you greater answer, right? So for this one, state the charge stored on any one plate. Okay, so till this point we have 90 microcoulomb of charge. Okay, so till this point we have 90 coulomb of charge, right? And if you can see that 12 is basically the two-third, and 18 is basically two three-third, maybe. So 6, 7, 8. So one third. Or just a bit. Just a bit. Okay, so this is a concept. Okay, now if we want to find the charge store on the 12-volt capacitor, so what should we do? We basically consider this circuit. Okay, we basically consider this circuit, the circuit on the right, this circuit. Okay, and we'll allow the current to flow in it. Okay, we know that the first capacitor has a capacitance value of 15 microfarad over X. The second thing is, okay, so I have, wait. If I just to write Q equals to CV, Q is equals to CB, and in place of Q, I have 90 microcoulomb, okay, divided by, in the 6, I have the voltage known, while the capacitance is unknown, and the voltage is going to be 9. So the charge, sorry, it should be multiplied. So the charge will be Q is equals to 9 times 9, 81. So 8.1 exponent negative 4, right? This is the charge stored on any one plate of the capacitor. Okay. So, wait. There's one problem. One problem. Okay. So we know the charge that is 90 microcoulomb and we know that it's capacitance. Okay. So we have to find out this. So 15 and 90. Okay. So 15 microcoulomb, or I have 90 microcoulomb. We are interested in 90. Okay. 90, and you can just put coulombs should be 90, not 80. Okay. So yeah, these two things goes off. So you'll be left with 90 divided by 15, and you'll end up getting 4. 2s are, 3s are, and 6 are. So V equals to 6. Okay. So basically, this is the voltage that you're getting across 15 microfarad capacitor, right? And now you can also do the ratio method over here, but it would get you in trouble. So just skip it. Okay. Now, the last thing is, so if we have the voltage 3 across it, so there will be 6-volt drop across here. Okay. And for that 6 volt, I can again use the concept Q is equals to CV. Okay. So in place of Q, we are now interested. Okay. And in place of C, if I'm working with 12 microfarad into the voltage that is remaining, which is 6. So the charge become um 72 microcoulomb. Okay. So this is the charge we are getting. Okay. And that is the charge across a 12 microfarad capacitor, right? Now, if I have to find the determine the PD across the 18 microfarad capacitor. Okay. So we found out that the potential difference across both capacitor is 3. Sorry, is 6, right? Because 3 will be 3 was across this point, so rest of the 6 L is right here, right? So we can say that you can just write down. Okay, you can just write down um 6. Okay, that's it. Okay. So we have done the concept of the second thing, and that is the series in the parallel concept of the capacitors, right? Right now, I'm stopping the class right here, and in tomorrow's class we'll be doing them of the questions, and then we move on. Okay, then that's it. Then okay, bacho, take care, guys. Allah Hafiz.
Love it, sir.
Hafiz.